There is an experiment that has been run thousands of times in hundreds of labs, and it should not be possible. Fire a single particle of light at a wall with two thin slits cut into it, and it behaves like a wave, passing through both slits at once and interfering with itself, painting a pattern of stripes on the screen behind. But put a detector at the slits to see which one it actually goes through, and the particle stops behaving like a wave entirely. It picks one slit. The stripes vanish.
Nothing about the wall changes. Nothing about the light source changes. The only thing that changes is whether something is watching. This is not a metaphor for how attention shapes perception. It is a measured, repeatable result in physics, and it has forced some of the most rigorous scientists of the 20th century to ask a question they never expected to take seriously. Does looking at something change what it is? Picture yourself as the particle for a moment. You leave the source with no fixed path, a smear of possibility spread across space. Ahead sit two open doors. In every version of this story where no one is watching, you appear to walk through both at once, and the two versions of you interfere with each other on the far wall, like ripples from two stones dropped in the same pond. But the instant a detector is placed at one of those doors, only one door exists for you now. The ripple collapses into a single point.
Physicists first cornered this in 1801, when Thomas Young split a beam of light and produced interference stripes, proving light behaved as a wave. The real strangeness arrived when the experiment was repeated one particle at a time. In 1974, researchers at the University of Milan fired individual electrons through a double slit and watched the interference pattern build up dot by dot, each electron somehow interfering with itself. In 1989, physicist Akira Tonomura refined the experiment using electron holography, and the result held. Unmeasured, each electron behaves like a wave spread across both paths, until it's measured. Then it snaps into a single, definite trajectory. Niels Bohr built an entire interpretation of quantum mechanics around this. He argued a particle doesn't have a definite position until something forces it to choose. Not that we don't know the answer yet, that there is no answer yet. Here's where it gets stranger. In 1961, physicist Eugene Wigner proposed a thought experiment that made this impossible to ignore. Imagine a friend, alone in a sealed lab, measuring a particle. From your friend's perspective, the result is already settled. But from outside, with no way to know what they saw, the entire lab exists in a haze of every possible outcome at once, unresolved until you open the door and ask. Wigner wondered aloud whether consciousness itself might be the one thing capable of finally collapsing a possibility into a fact. Then, in 1978, physicist John Wheeler pushed it further with the delayed choice experiment. What if you decided whether to measure a particle's path after it had already passed through the slits? In 2007, a French team led by Vincent Jacques built this for real, using photons and a detector that switched on after the particle had already traveled past the slits. The result matched Wheeler's prediction. The photon's past behavior seemed to depend on a choice made after the fact, as if observation reached backward and decided it.
So, is consciousness the missing ingredient reality has been waiting on? Here's the part most retellings leave out. Through the 1970s and 80s, physicist Wojciech Zurek developed a theory called decoherence, and it tells a very different story. A particle doesn't need a mind or an eye to lose its wave-like behavior. It only needs to interact with its environment. Air molecules, stray photons, anything that carries away information about which path it took. Once that happens, the interference disappears, whether or not a conscious being ever looks at the result. A rock in open air, constantly bumped by trillions of molecules, never holds on to quantum weirdness long enough for anyone to notice. Consciousness has nothing to do with it.
That reframes the whole story. Decoherence explains why we don't see large objects behave like waves, but it doesn't fully explain why measurement resolves possibility into one outcome instead of another in the first place, and physicists still argue about that today. So the honest answer sits somewhere between the mystical version and the purely mechanical one.
reality does seem to behave differently depending on whether something interacts closely enough to know the answer. It may just not require a mind to do it. If a photon can seem to wait before deciding what it was, what does that say about the things you're sure already happened today? Tell me in the comments what you think decides the difference. A conscious mind or just enough atoms bumping into each other? And if this kind of question keeps you up at night in a good way, subscribe, because Science Scry digs into one of these every week.